Hey, good evening. Welcome to another webinar from the Talent Q seminars that we have every Tuesday, or with like every Tuesday, every 15 days. We will wait a couple of minutes to other people to enter, but in the meantime, I have to say thanks to Almudena for accepting our invitation to present her great work about combining two QPUs that they have made a classical link between both of them in order to calculate a bigger problem that they cannot solve using a single QPU. That is called usually distributed quantum computing, but in this case without yet the quantum communications. Let me introduce her. Almudena is research staff at IBM Research Zurich. Previously, he studied in the University of Manchester the Bachelor in Mathematics and Computer Science. After a small time working in a company, I think, Almudena moved to ETH in Zurich in order to study the Master in Mathematics, and from there she moved to IBM Research to make her PhD. First of all, the master thesis about quantum algorithm for solving 3D diagonal linear systems of equations. Pretty nice work. If you don't know it, maybe it deserves that you read it. And finally, she did her PhD again in the IBM Research Zurich and ETH Zurich about the extrapolation methods in quantum computing. I was looking around in internet and I discovered that she is also inventor in the of 3 patents regarding of state initialization for quantum amplitude estimation or using quantum amplitude estimation. Congratulations about these patents. And today she will talk us about the last paper that they have in Nature that is titled Combining Quantum Processors with Real-Time Classical Communications. For the attendees, initially you cannot speak for making questions, but if you want to make questions, you can use the chat, or later at the end, we will ask you to raise your virtual hand, and in this case, Javier Bouzas, that is helping me in this seminar, will open your microphone so that you can ask Almudena. So again, Almudena, thank you very much for joining us in this webinar. The floor is yours.
Thank you. So thanks for the introduction. Today I will be presenting the result on combining quantum processors in real time. And first of all, why did we look into this? The main motivation is that current devices have limited connectivity. So this has limitations not just because if you have an algorithm that requires, for example, using connecting qubits that are between, say, here and here, then if you want to implement something connecting them, you would have to add a lot of swap gates, which means a lot of CNOF gates, which means a lot of 2-qubit gates, which contain more noise, and therefore your algorithm will become more noisy. So that was one motivation. And then the other one is that the number of qubits itself is limited, which will limit the size of the algorithms you can run. So the goal in the future is to be able to run some sort of distributed computer where instead of having one chip with a lot of qubits, you have a number of chips, each of them with a number of qubits that it's sustainable to develop. So that was kind of the motivation. And the talk today will be structured as follows. First, I will present the theory of circuit knitting, both with only local operations and with local operations and classical communications. So in the paper, what we did, it was to compare both methods, because theoretically, one compared to the other might give some advantages, But then when you try to implement these things in practice, we realize that you have to take into account other things. And that's something I want to comment into. And then how we error mitigated this type of circuits. And then I will present the main results. So the first one was to engineer periodic boundary conditions. So that means, for example, connecting qubits that are very far apart in the chip, which if it weren't for the circuit knitting techniques, we would need to implement it via a lot of 2-qubit gates. And the final and maybe the reason why this paper is known, which is connecting 2 different QPUs via classical communication. So that will be the final result that I'm going to present. So first of all, what is circuit cutting or circuit knitting? So suppose for simplicity that we have a quantum circuit on 4 qubits, and we only have available 2-qubit devices. And say we want to run something like that. Now, if that were the case, we have a problem because this gate here would be across the 2 different chips that we have. So how can we run something like that? So the idea is as follows. We can write any 2-qubit gate as a linear combination of operations that are local to the 2 subsets A and B of 2 qubits. So these are single qubit operations, and this is something we can always do. We can write it as this linear combination. Now, we've rewritten a unitary gate into a linear combination of other gates that we can implement and that are only spanning the subsets A and B. So now the question is, how do we implement a linear combination? So the idea will be to run not one, but several circuits. So for each of the I's, we are going to run a separate circuit. And then we will measure some expectation value and we will combine these things classically by appending the weight to it. This will do it classically. So how do we do it more precisely? We can rewrite this linear combination as follows. We take the sign away, then we write the one norm of the weights, we call it gamma, and we take it out. So and what is left is a probability distribution. So if you say sine of AI times gamma times the absolute value of AI divided by gamma, that's the PI, and that's a valid probability distribution. And why do we want to write it this way? So there will be 2 different ways to implement it. You can either implement each of the separate circuits and then do the linear combination classically, but then the price to pay is a higher variance, or you can sample from this probability distribution, and whenever you sample the circuit with I, you implement the circuit, and then you classically append the sign of AI times the gamma and multiply it to the value that you observe. And this is beneficial because now the price that you have to pay is that the number of circuits gets increased by this gamma squared. If you were instead to run each of the different circuits and combine it, then you will get here an extra, the number of circuits factor. So say there are a total of k circuits, you would get an extra k. So that's why we sample instead of just enumerating all of them. So as I said, the price to pay is this extra number of circuits that we need to sample. And the reason is because the variance gets amplified. So we need the price to pay for cutting is that you need to run more circuits, basically. Now, what happens if instead of cutting one gate, we want to cut k gates? Then the price is multiplicative. So then the number of extra circuits that we have to run is not gamma squared, but gamma to the power of 2k. So what this means is that you cannot take just a circuit and cut every single one of the 2-qubit gates and then obtain circuits with only single qubit gates, because that you could simulate it classically. And you cannot do that because then the price you have to pay is exponential, basically. So this is telling you is that circuit cutting is a very powerful technique, but it's also expensive. So you should use it sparingly. Now, what I've presented here is only local operations, meaning that they are local to each subset. There is no classical communication here at all. And the next question would be, what if we include classical communication? So one key point here is that the number of linear combinations that we can rewrite U as is infinite, or there are many possible linear combinations. And because the price that you need to pay it's related to the weights, you want to find a basis such that this gamma is minimized. So basically the question is, can we make this price that we have to pay cheaper by using classical communication? And this is what we know as the LOCC approach, so local operations with classical communications. And originally, at the time as we started the paper, the answer was yes. You can achieve a lower gamma by taking classical communication in the picture. However, as I will show you later, gamma itself doesn't tell the whole story. So theoretically, it should be cheaper if your gamma is lower. In practice, because there is compilation, there is noise from the gates, it's not everything about gamma. So an example of how we cut with local operations is taking a control set gate. So a control set gate can be written as a sum of these 6 different circuits, where now the AIs are these -1/2 or 1/2. Now the cost of this decomposition is gamma equals 3. I mean, the sampling overhead is gamma squared, but for simplicity, I always just write gamma. Now, in practice, something that I just want to mention is that later research paper by people in our group, they found that there exist better decompositions that do not require classical communications and that they are as cheap as with classical communication. However, there is a but here. And as you can see, these circuits, they are extremely simple. So it's either single qubit gates or measurement. These newer decompositions, they require ancilla qubits and more measurements. So while the gamma itself is lower, it requires some other resources. So in this work here, we focus on what is known as the meter-eye basis, which is the one I'm showing here that it's very easy to implement. Now, there is one more thing in this picture, and it's that I grouped the 6 circuits into 3 different templates. The reason I did that is because in practical or in real life, when we run circuits, we have to compile them. So the way it works is that you create your circuit and you send it to the quantum device. And in the process, this circuit needs to be compiled, and that takes time. In parallel, as we were developing this work, the people from the hardware were developing what is called as parametrized circuits, meaning that you can have a template with some parameterized gates that only needs to be compiled once. And then you can send it several parameters that can be updated into the template itself, but these things only needs to be compiled once. And now the reason I'm saying this is because here, when you run a circuit cutting, usually you need to sample, say you wanted to run something with 1,000 salts. Originally, that would mean compiling a circuit 1,000 times. Now, because we have these templates, if you only have one template, you would only need to compile it once. And in this case, we only need to compile at most 3 different circuits. So that's what I mean by practical implications, that with this cutting approach, we only had to compile 3 different templates, which has implications into how fast you can run things. The other thing to notice here is that only 4 out of the 6 circuits contain mid-circuit measurements. And the reason I'm saying this, again, is in our quantum computers, single qubit gates, they are fast and they are not noiseless, but the noise level is an order of magnitude less than 2 qubit gates. And measurements, they are also pretty noisy. And they are not just noisy, but they take longer to implement because once you measure, there is a delay between the time you measure and the time you can implement the next instruction. So they make the whole duration of the circuit slightly longer, which also needs to be taken into account, especially if you are running 1,000 circuits because you are taking 1,000 salts or even more. Now, that was for the LO case, so only with local operations. So how do we cut a C-set gate with classical communication? So the idea is as follows. First of all, we can write a CNOT gate with a teleportation circuit like this, where you consume a bell pair, which is this thing here. So you need 2 extra qubits to create entanglement. And then using measurements and feed-forward instructions, you can simulate the CNOT gate that originally was between these 2 qubits. Now, right now, it seems that I just made more complicated implementation of a CNOT gate And moreover, I still didn't cut anything because all these qubits are connected in the picture. However, the idea is that we can cut the CNOT gate here, and therefore we can separate the 4 qubits into 2 subsets of 2 qubits, because this is just instructions that are implemented from a classical bit string, so there is no connection between this qubit and this qubit. So the idea would be to cut the CNOT gate from the developer implementation. And the way we do it is as follows. We create a parameterized circuit that only requires these single qubit unitary gates that are parameterized. And then we have we've got the measurements with some feed-forward instructions. So this is what it's called the classical communication, because you measured, and based on what you measured, you implement, in this case, the X gate. If you see a 1, and if you see a 0, then this is not implemented. Now, the price to pay for cutting this CNOT gate with classical communication is just as before, that we have to implement more circuits. So, what happens if we want to cut not just one CNOT gate, but 2 of them? So in this picture here, we want to implement the purple and the red subsets in, like, say, 2 different quantum devices. So this technique becomes cheaper as you try to cut more and more gates. So the gamma price for cutting one pair is 3. If you remember from the case with local operations, the gamma was 3, so there is no difference. However, if you want to cut 2 pairs, then the gamma goes a bit lower to 2.65, which means that in the yellow case, the price of cutting 2 gates would be 3 to the power of 4. And now in the case with classical communication, it would be this 2.65 to the power of 4. So that's cheaper. If you have 3 pairs, it would be 2.46, 0.47 to the power of 6 versus 3 to the power of 6. And if you want to know what happens if you go to the limit of cutting an infinite number of pairs, then it goes down to 3. So it does become cheaper indeed in terms of the overhead that you need to implement this technique. Now, how does the circuit look like? It becomes this parameterized template with now all these gates for cutting 2 different bell pairs. And how we can find the parameters for these gates, we did that via an optimization problem that we only had to run once. So how does this work in practice? This bit here where you measure something and then implement some quantum gate based on some classical instruction. So it works as follows. So this is for the case of a single pair with 2 measurements. There are 4 possible cases: the 0, 0, 0, 1, 1, 0, and 1, 1. So in this case, say when we see a 1 here, then we implement the X gate. If we see a 0, we don't. And same here. When we see a 1, then we implement the Z gate. And if we see a 0, then we do not implement it. So the way it works is the mid-circuit measurement here, it's implemented in some sort of lookup table where the measurements are performed, and then the electronics, they look up into a table that looks something like that. So in the case where it's a 0 here, 1 here, then only the X gate is implemented. And in the case both are 1, for example, then both the Z and the X are implemented. And having this lookup table allows to have an O1 time to look up in which case are we. So this is the case with only 1 bell pair, but if we want to cut 4 gates, then we would end up with 256 possibilities. So this translates basically into waiting time. So the problem with this type of circuit is that between the measurement is performed and the classical instruction is implemented, there is some delay. And delays in a circuit, they are basically bad because whenever you have idle qubits, then you get noise. So one way to get around this is to implement dynamical decoupling into these points in time where your qubits are idle. And we went one step ahead and we developed a technique to use zero noise extrapolation applied to the delay that you get between the measurement and the implementation of the feed-forward instructions. So what we did is as follows. We ran several circuits where we first just implemented the dynamical decoupling sequence that you can see here. And then because you cannot make the delay shorter, but you can always make things worse, so you can insert additional delays. What we run is several circuits with extra delay, which is inserted here with this delta here. So by running circuits for increasing delta, we in practice increase the noise, and then by plotting them and fitting the data points to a line, we extrapolate it to the zero noise value of the switch. So that's how we mitigated the extra noise that the LOCC circuits had due to this measurement and feed-forward instructions. Now, in terms of results, the first result that I wanted to show is periodic boundary conditions. So first of all, in all cases, we are looking into implementing graph states. So a graph state is given a graph with some vertices and edges. You can implement the graph state as follows. You can identify the vertices with qubits. So you have here from 0 to 4. And then you apply Hadamard gates at the beginning to all the qubits or all the vertices. And then for each edge, you apply a C set gate, so a control set gate. So for example, there is an edge between 2 and 4, and here you can see a gate between 2 and 4. And now, so okay, we have implemented that graph state. So then what we want to measure is how good its implementation was. And to do that, we define the stabilizers of the graph, which are defined as an X measurement on the qubit I and Z measurement on the remaining qubits. And the stabilizers have the property that the expectation value is always 1. So we know a priori that we need to get a value of 1. And if we see something and it's not 1, we know that it's because of the noise. So what we want to do is cut some of these edges, because the goal will be to implement graph states that corresponds to graphs that maybe are not native to the device. So how do we cut an edge? And here we have an example where here we cut the 1 to 2 edge. So that corresponds to this line here. So in the case of LO, if you remember the circuits, they all have weights either 1/2 or -1/2. And then we had 3 possible templates: the one with only single qubit gates, the one with one measurement and a single qubit gate, or single qubit gate and measurement. So in this case, we would run, or we would sample from these circuits, which all have the same sampling probability because the weights in absolute value are the same. And then we run several circuits, we compute the expectation values at the end, and we combine according to the weights here. Now, for the case with classical communication, it's very similar. We have in this case only one template, which would correspond to parameterized gate for the additional 2 qubit gates that we need to implement the bell pair, and then the measurements with some feed-forward instructions. And that would correspond to the cut edge. So in the very first test that we had was a graph with periodic boundary conditions. So in this case, we had here the chip, and we identified the vertices here at the very end with the ones at the top. And what you obtain by doing that is this kind of cylinder here. If you were to implement something like this without cutting, you would need swap gates that go all the way from here to here. So this incurs a very large overhead. Now, we had to define a way to know how good our implementation was, and this is what we call the edge witness. So the edge witness, it's based on the stabilizer that I defined before, where we measure stabilizers on different vertices. And then the edge witness that is assigned to a given edge, it's calculated from the stabilizer values from the adjacent vertices. Now, the main property of this edge witness is that it should be less than 0 whenever there is entanglement. So in this case, for example, if everything goes according to plan, so if everything is 1, this would be 1 plus 1 plus 1 equals 3. So the witness should be -1/2. That's the ideal value. Now, because we want to take into account statistics, we basically defined this statistical test, which gives you a negative value whenever the witness is below 1, and B, the expectation value is good enough and the variance is under control. So basically, in this case, if you plug in the ideal value, this would cancel out because it would be -1/2 plus 1/2, 0. Then you would get -1/2. And then you have this penalty value here, which is proportional to the variance of the witness. So then we run 4 different cases. The first one is to try to implement the periodic boundary conditions with swap gates. So swapping gates, if we wanted to identify this vertex here with this, we would have to implement it via swap gates. And this would require an extra 262 synod gates. And each of them has a 1% error. So you can imagine that this type of circuits will have a very large amount of noise. Then secondly, we try to implement it via cutting with classical communication. So in this case, we need 27 extra circuits, and the gamma is 2.65 in this case because we are cutting 2 gates. Now, you might be wondering why cutting 2 gates, because there are 4 edges here. The reason is because we do 4 cuts, but because they are quite far away, we can do them in parallel. So it's the cost of cutting 2, but we are cutting 4 gates. And in the case of LOCC, we need 8 additional qubits to create these bell pairs. Next, we do it with only local operations because we want to, basically the idea was to compare these 2 approaches with or without classical communication. And now in the case of only local operations, the gamma value, so the cost of cutting, is slightly higher, it's 3. However, it doesn't require additional qubits, and you only need mid-circuit measurements, meaning that you do not need these feed-forward instructions, which are quite costly in terms of the delays. And finally, we also compare to just not implemented DH at all. So here you would expect that the rest of the graph is really good, but you are not implementing the exact graph. So how did things go? So these are the results first for the dropped edge. So here we have the nodes that are involved in some cut gates, and you can here see that the stabilizer value, it's 0 because we did not implement it at all. But for the other nodes, the stabilizer was pretty good because, as I said, it doesn't require so many gates in the end because we are not implementing the cut. We are not implementing the edges that are among vertices that are very far apart. And now this plot below, it corresponds to the witness value, where if you remember, being negative, it's a good thing. It means that there is entanglement. And as you can expect, because we did not implement it, for the cut edges, it's positive, there is no entanglement. And for the edges next to the cut, there is also no entanglement because we did not implement it. Next, we have the case with swap gates. So there is no cutting in this case, it's just a lot of additional gates. So now the stabilizers, they are closer to 1, but they are pretty noisy. And the stabilizer corresponding to vertices that are farther away from the cut, they are also quite noisy. That's because the whole circuit contains a lot of single gates. And for the witness value, some of them are a bit negative, but still the results were pretty bad, and this is only due to noise. While in the case of the dropped edge, it's very bad, but it's just because it was not implemented. Now, here we have in green the case for the local operations with classical communication. And there are 2 things in this plot. the first one, the full green color, that just corresponds to the raw data. And then this green with white in the middle, that corresponds to the extrapolated value. So remember that we are trying to mitigate the error arising from the extra delay that comes from these dynamic instructions. So now you can see that the results are a lot better. So in the case of vertices that lie in cut edges, now the stabilizers are very close to 1. They are better than the case with swaps. And moreover, the witness value is consistently negative. So that's a good thing. And we also implemented it with local operations, and this is even better. So there is a bit less noise. The stabilizers are very close to 1. And again, the witness value is also all negative, which is what you would expect to see. So it means that we created entanglement via cutting. So to summarize the results here, we created a graph state with boundary conditions, which is a non-hardware native, for a total of 116 gates. Now, if you remember this witness statistical test that I presented you before, that defines the success metric. In case of implementing the full graph with swaps, the success rate was 70%, and that's because it requires a lot of gates. Then for LOCC and LO, so the two cutting frameworks, the success rate was 100% because we successfully created entanglement across all edges. And in case of the dropped edge, it was 89% because the remaining 11% corresponds to the cut edges, and they fail simply because they are missing. So more details. These are the edges for the swap case. These were the edges that had no entanglement. The ones in pink. Then for the LOCC, as you can see, they are in black because we created entanglement in all of them. And for the dropped case, there was no entanglement in everything that was around the cut gates because they were not created. Now this is the point that I mentioned before, that we were comparing the two approaches, so with and without classical communication, in the sense that not everything is based on gamma. So theoretically, you would expect that the variance of the LO approach should be 1.60 times higher than the variance from the LOCC approach. This is from the theory. However, in practice, we measured that it was only increased by 1.49. So why do we think this is the case? So why does the variance of LO is not as high as it should be as predicted by the theory? So we attribute the difference to different device conditions, because it just happens that the hardware changes with time. And it could be that when we run the LO case, it was slightly better than when we run it for the LOCC case. But we also think it's due to the LOCC circuits having more noise, due to having more measurements and having these feed-forward instructions. However, in all cases, the variance was under quality control, which was what we consider successful. Now, the final test was to create a graph state that would span 2 different QPUs, which is maybe the result why you are here for. So the idea was to create a graph state over 134 nodes. Now, each of these QPUs contain 127 qubits. And what we did was identify the qubits here that you see on the edges. Now, instead of identified with each other, we identify them with the same thing, but on a different chip. So again, we are creating a kind of cylinder graph, but now it's a bigger cylinder graph that requires 2 different chips. So in terms of how different techniques perform, now note that we do not have the swap test, simply because we cannot implement via swap gates something spanning 2 different devices. So in this case, the LO approach outperformed the other 2, and the LOCC approach still outperformed not implementing the edges. So the way to read this graph is that the more to the left the lines are, the better the result. Similarly, this is for the witness value. So this is if you remember, the metric that defines success and that takes into account the variance. And in the case both of LO and LOCC, we achieved what we defined as success. For the swap case, it was not possible to implement, and for the drop edge, it was a 91% success rate. So again, we did a comparison of the variance. Again, similarly as before, from the theory, you would expect that the LO case should have an increased variance compared to LOCC. However, we measured an even smaller increase than last time. So before it was 1 point something, and now we measured 0.91 increase, which is actually a decrease. And we attribute this to, again, more noise on the LOCC circuits, because the more noise a circuit has, the more variance the result will have. And then we really think in this case it was because the device was just better. And one key point that was pointing us towards the device being better is that cutting was even better than the dropped edge case, even for the stabilizers on non-cut edges. And so it was basically having a bit of luck for this one run. And however, we still need to study better these variants, because this study is purely from an experimental point of view. Now, one more thing that one could look into is into dynamical decoupling sequences. So for the LOCC case, you are implementing instructions that require measuring something, waiting because you need to connect to the electronics, and they need to check in this lookup table, and in the meantime the qubits are idle. And for that, good dynamical sequences are important. And we looked a lot into that. However, a bit later, one of my co-authors, they had another paper on good dynamical decoupling sequences. And the thing is, this really depends on the device as well. So you need to design a dynamical decoupling sequence that is good for the application that you have and also for the device. So in summary, what we did is we did a first demonstration of LOCC on hardware, which had not done before. And to do so, we created periodic boundary conditions, both with LOCC and with LO, on a graph with 103 qubits. And we also created another graph state on 2 connected QPUs that were connected with real-time classical communication. And so this one requiring more than a single eagle device. In terms of how they compare to each other, so LO requires more circuits because it has a higher gamma than LOCC from a theory point of view. But as we saw, the circuits required by LO are a bit simpler. So at the moment, unless the hardware improves, if you have an application, you need to consider whether it's more beneficial to use LO, because maybe in practice the overhead will be lower simply because the circuits are less noisy. Then in the future, we would like to look into an applications of circuit cutting into maybe some more applied context rather than just creating a graph state. There also needs to be a more systematic investigation of the variance. And then we need improved error mitigation, both on mid-circuit measurements and feed-forward. Because for this paper, we only try to mitigate the delay for the LOCC part, but we did no more mitigation. Then in terms of dynamical decoupling, we need noise-tailored sequences, and then maybe also gapless dynamical decoupling. So gapless means that it's continuous rather than implementing sequential gates. Now, that's all I wanted to present, and I would be happy to take any questions.
Hello, Almudena. Thank you very much for your presentation. That was very interesting. We have at least one question from Guillermo, I think. So, Javier, if you open the microphone for Guillermo.
Yeah. Guillermo, please go ahead.
Okay. Can you hear me now? Yes. So I have a couple of questions, and first of all, I excellent work. I mean, I liked it a lot because I also tried recently to do some circuit cutting myself, try to code this, and it's a difficult amount of code. I know that IBM has some tools for this, and I would like to ask you about the use of these tools because I know there's a package or sort. I don't know if you, for this work, have you used some tools that are already available, or is like more still development level?
No, so I think the tools now, they should be available. We did not use them. The reason is because this was a project that started maybe early 2023. I don't quite remember, but basically it started kind of in parallel to the development that you are talking about.
Okay, and then I have a couple of more questions about the something you said at the beginning of the talk. That you say when you have these different circuits that you can have a template or whatever, but there's this way of sampling instead of running all of the circuits. So you're sampling from a distribution or something like that. So what I intended to do is knowing because each circuit can have some, let's say, some weight. Sometimes it's positive, sometimes it's negative, but the weight is square of that or the absolute value of that weight, whatever. So how to say, like distributing the number of shots to each one of the circuits. So if I have a budget, I don't know, 1,000 shots. So I don't know, some shots for one circuit, some shots for other circuit, some shots for another circuit. But what you said you were doing is different. So just you have a distribution as your sample from that distribution. Could you elaborate on that because I didn't get it?
Yes, so that's a mathematical argument. It's not only for circuit cutting. It's there is a very good review on error mitigation methods, and it's written there, the mathematical argument. I don't remember the name of the paper right now, but basically say you have a linear combination, and you want to implement it via running the circuits and then like weighting the circuits with the weights of the linear combination. There is always the variance argument, and you can either run them all and just combine the results or sample from them. And it just happens that if the weights are not the same, then it's always better to sample. And it's some kind of argument that has to do with the triangle inequality, basically.
Okay.
And I would be happy to point the paper out because the mathematical proof is there.
I would love that. If you could, I could send you an email or something like that just for asking you for this paper. I would be very thankful. And just, I don't know if I can have just another question, but I don't know if there is somebody else who wants to ask something. But it's just about the variance analysis. Very quickly, just I see that there's some distributions of the variance, and sometimes I just say, oh, with LOCC, the variance is smaller, and the variance with LO is larger, so it's sometimes or something like that. But what I didn't get is where does this distribution came from? Because you're always cutting the same circuit, so you do it a lot of times and then look at the overhead, or how what is that? The stabilizer varies.
Yes, I mean, you're measuring a stabilizer, but you don't measure it with one shot. You measure it with, I don't remember, say 10,000 shots. So then you get these error bars, and the error bars are what you are seeing here.
It's for different observables or something. Okay.
So I don't remember, say like you are measuring 25 stabilizers. Then that means that 5 of them had like 10% variance. Kind of that's the argument.
Okay, I cannot get it. Wait, thank you. That was all for me, but
Okay, and now it's time for Miguel Carrasco.
Yes. Hello, do you hear me?
Yes.
Okay. Well, first, thanks for the talk, Almudena. It was very interesting. I was wondering if there's a particular reason for choosing this graph state, because since your hardware doesn't have like a full connectivity, you could choose a lot of combinations of two qubit gates to cut. But yet, for me, it's like a very particular like kind of state that you prepared?
Yeah. So basically, the goal of the paper was to implement a LO and the LOCC techniques.
Almudena, are you there? It seems that we lost. Okay, Almudena. Okay, now you're back.
Okay, sorry. Yes, so as you said, we could have chosen anything, but the reason we just wanted to show the implementation of LO and LOCC in practice. And we could have done it with any type of circuit. And the reason to choose a graph state is because A is very easy to prepare, and B, it is very easy to check whether the entanglement is there or not there. That was the reason.
Okay. So besides that, there's not anything in particular. Okay.
No. So that's why also one of the future goals is to use circuit cutting into an application, like some practical application.
Okay. Thank you very much.
And Palacios, I think that is the next one.
Anna?
Okay. Hi, can you hear me?
Yes. Yeah.
Thank you. Thank you for the nice talk. I had a question regarding the lookup tables that you were mentioning for the LOCC approach. So this kind of limits, I guess, because if you're doing a lookup table, then you'll typically run into memory issues, I guess, if you want to cut like large things. I don't know if this is... Have you thought about this in terms of scalability, or how would you recommend it? Does this kind of mean that you will always be sparsely connecting chips, or?
So, I mean, this kind of switch instruction or lookup table, again, it's something that was developed at the same time, and it still needs to be improved because it's not the optimal way. But also, like, you should not be cutting an insane amount of gates simply because then the cost from the gamma is going to be very large. So cutting is this technique that you want to use very sparingly. So for example, say you have a circuit that has maybe one long entangling gate, or maybe it has like only a few gates that connect two different subsets and therefore you can split them. But the idea will never be to cut, like say, half of the gates.
All right, thank you.
More questions
There is one question in the
in the chat.
Q&A. Yeah.
Let me check. I don't have any question. Maybe Javier, you can read the
read it.
question. Okay.
Marta Losada is asking, how did you program dynamic circuits and control flow across the system?
So, okay, it was an effort with experimental people, but at the moment in Qiskit, you can very easily create dynamic circuits. I think it's something that it should be, if you Google Qiskit in dynamic circuit, it should be there, but it's something like in Python, if whatever you implement some classical instruction, or if not, then implement another one. It should be Qiskit if test or something along those lines. So it's something we did from Python. We did not implement it physically. That was more from the experimental people, and you can use it today.
Let me introduce a variation of this question because I'm curious about that. You can execute your case using a single circuit that you execute part of the circuit in one QPU and part of the circuit in another QPU, but being a single circuit instead. Or you can executing in parallel two circuits that must communicate between them. So what is the technique that you finally use? Using a single circuit with half of the qubits in one QPU and half the qubits in another QPU? Because in this case, it's very easy. Well, very easy. Sorry. It's, you can use the dynamic circuits without any modification of your technology, or you are running two parallel programs.
We created a big circuit that then was split into two circuits, one that was sent to one QPU and the one that was sent to another QPU.
Okay. So and how coordinate the readouts between one the measurement that you are doing in one QPU? You have to pass the information to the another one through the classical cache or something like that inside the system.
Yes, so these chips, I think there is a nice picture in here. So I mean, they are in the same fridge, I think.
Uh-huh.
And then there is some a device electronic that can communicate with both of them. So the subcircuits, they are happening in parallel, and then you perform a measurement. The measurement is read by some electronic chip, and then based on the classical bit that it's read, then it will send some instruction to the other one.
Yeah, but you don't have any special instruction in your limits to wait for this readout from one circuit to execute one instruction with another one.
No. So from a user point of view, you are just designing a normal circuit with dynamic instructions.
Okay.
It's only that if you wanted to work with two different QPUs, they have to be in the same fridge and they have to be connected somehow.
Okay. More questions? Well, it seems that we don't have more questions. Thanks again, Almudena, for this. I know we have one question, last minute question. Jorge?
Yeah, sorry. This is about the last question that Andres made. Do you have any clue how they are synchronized? Or this is just low-level hardware programming almost? Thank you very much.
No, I don't know the details of the hardware part. I come more from the theoretical perspective. From our side, it was, as I said, just running a normal quantum circuit program. You wouldn't be able to see it from the user perspective. So I don't know how the inside it works.
Okay, thank you.
30 seconds for waiting for the next one. No more questions? Is it like a good thing? No. Okay, so again, Almudena, thank you very much for this nice talk. You did a very nice work that is opening now new possibilities to the quantum computers and to expand the number of qubits for calculating more things with chips smaller or small chips. And I think that it was a pleasure to have you here and hear you, and hope that in the future you will have another opportunity to talk in these webinars. That's all. Thank you very much for the attendees and for the people that did questions. We hope to see you again in 15 days with the next webinar that Javier, maybe you can remember us, which is the next one.
Yeah, Davide. Davide from
University of... Well, we have now a question. Maybe it's too late. Sorry. Maybe you can send us the questions by email to Quantum Spain and the Talent Q program, and we transfer Almudena these questions because we have to close at this moment the session. And again, thank you very much to the attendees, and thank you very much to Almudena. I hope to see you soon. Bye.
Thank you.
Bye.